record this. Let me minimize this. And let me blow this up so that we can see it. What kind of cell phone did you take this picture with?
iPhone 5, I think it is.
Okay.
Yeah.
Make sure when you send it as a large picture instead of small or medium. It seems to affect the resolution quite a bit.
Do we need to resend it, David?
No, I can read it. I can read it. It's just not up to typical iPhone standards. So I figured maybe something happened, but all right, let's start with number 1. How do we solve that? We have 5x over 4 equals 35 over 8.
Didn't you just cross multiply?
You could, but actually cross multiplying does an unnecessary step. In other words, what cross multiplying is multiplying both sides by 4 and then multiplying both sides by 8. Well, I could do that, but then I'm going to have to divide the side on the left by 8 again. So there's really, if you have your variable in the numerator, all you need to do is multiply both sides by 4, which gives us this. And now divide both sides by 5, which gives us that. You saw how I got to that?
Yeah.
Now we can do some canceling. That 5 and that 35, that becomes a 7. That 4 and that 8 becomes a 2. So it's equal to 7 halves. And notice the difference. You're not the only one that wants to cross multiply this. Everybody in the world wants to. It's okay to cross multiply it. I get this. And then I got to divide though. I just multiplied by the 8. Now I got to divide by 40. So it still gives you the same answer. And maybe not even extra steps. But just remember that when you have a fraction equals a fraction and your variable's in the numerator, you don't really need to cross multiply. You just need to get rid of that denominator and then get rid of that 5.
Okay.
All right. The next one, 15 over 3 equals x minus 3 over 5. And this is similar. There's really no reason to cross multiply. What should we just multiply both sides by?
Would it be 3?
Not 3. We're trying to isolate x.
So it'd be
You want to get rid of this denominator, and then you want to get rid of that number. Those are the two things we got to get rid of. And then what we'll be left with is just x. Okay, so if I multiply both sides by 5, I have 75 over 3 equals x minus 3. And what is this equal to? If you have 3/4 in your pocket, what do you have?
Oh, you have 25.
Okay, so 25 equals x minus 3, and now to get rid of that, we want to add 3 to both sides, so we get 23 equals x. Now notice how much easier this was rather than cross multiplying it. If I had cross multiplied it, I'd have had to do 75 equals 3 times x minus 3, and then I would have had to just divide both sides by 3 or distribute that, one or the other. Either is about the same. In other words, if I go ahead and divide both sides by 3, I've just done what I just did the opposite of what I just did. In other words, there's no point in multiplying by 3 if I got a very next step, divide by that same 3. You know what I'm saying?
Yeah.
Okay. Not that cross multiplying ever really hurts you there, other than maybe giving.
Waste time.
To make sure I got this one right. Yeah, I did. What's the first step here? Always, when you're looking at equations, always be looking to get rid of denominators.
So could you times by 2?
Which side?
You would times the left side by 2.
I could, but that won't get rid of the 4. What if I multiply the left side by 4 and the right side by 2?
I guess you can do that.
Excuse me, I'm sorry. I can multiply the left side by 4, but I got to multiply the right side by 4 also. And that will get rid of both denominators. In this particular case, cross-multiplying probably makes the most sense. It's as efficient as anything. Go ahead and cross-multiply and tell me what the next line is.
Would it be x parentheses minus 4?
Well, if I'm going to cross-multiply it, that's what the left side's going to look like.
2x minus 2.
And that's what the right side's going to look like. Okay, in other words, you need to add parentheses. Now you can distribute. In other words, now get rid of the parentheses. What's the new left?
Would it be x minus 4?
2x minus 4.
2x.
You have to multiply that times that, and you also have to multiply it by that. What's the right side?
4x plus 14. 4x plus 16.
Okay. Now I can move the 2x over to there, the 16 over to there, and I get minus 20 equals 2x, so x equals minus 10. All right. Let's look at number 4 here. The ratio, the measure of three angles is 4 to 5 to 6. Well, I can't just say 4, 5, and 6 because that does not add up to 180. But they're talking ratios. So if I add a variable like x, now I have 4x, 5x, and 6x. And notice what the ratio of those three angles is. It's 4 to 5 to 6 because the x's all cancel out. In other words, if I have 4x over 5x, the x's go away and that relationship is 4 to 5. By adding the x, I'm now able to create an equation that I can solve. What's the equation?
Wouldn't it be 4x plus 5x plus 6x equals 180?
Yeah, and that's the purpose of adding the x, is that now I can solve for x and figure out what the three angles are. So that's 15x equals 180. So x equals 12. So what are the three angles?
Would it be 48, 60, and 72?
Yeah, your arithmetic's getting much faster. Yeah, and it would be difficult to come up with those three if I didn't throw in that variable, which I kind of had to create, because they didn't give me this x as part of the problem. The sides of a rectangle are 7 to 8, and its perimeter is 270 cm. So how should I label these? Obviously, if I label that 7 and that 8, that doesn't give me a perimeter of 270. The right ratio, In other words, it gives me a rectangle whose ratios are in a relationship of 7 to 8, but what do I need to add?
Well, wouldn't you have to add x's?
Yeah, I need to do the same thing I did on the last problem. Now they're still in a 7 to 8 ratio. In other words, if I put them in a ratio like this, the x's go away, and there's my 7 to 8 ratio. So I haven't changed the ratio at all. But now I can write an equation. What is it?
Would it be 15x equals 270?
Almost. 15x is not the perimeter. What is the perimeter? In other words, if the bottom's 8x, that's got to be 8x, and if the left side is 7x, that's got to be 7x.
Would it be 14x plus 16x?
Yeah, so 270 equals 30x, which makes x equal 9. And now you know the sides of its 7x. Since x is 9, that's 63. This is 8x, so this must be 72. And now that and that are in a 7 to 8 ratio, and my perimeter is 270. Whereas these two add to 135, and it's twice those. So very similar problem as the last one. All right, let me blow this up just a little. I'm having a little hard time seeing these two triangles here.
Did we skip to number 10? I feel pretty confident.
Sure.
From 6 to 9, but number 10 gave me a...
Okay.
Pro.
There's a theorem in geometry for number 10 that says that if you have this line that bisects that angle, then the relationship of this side to that side is the same as the relationship 3 to x. In other words, I can say 9 is to 15 as 3 is to x. And the most important thing here is make sure you get the order right. It's not 9 is to 15 as x is to 3. We can clearly see that x is the bigger side. So you want the smaller to the larger equals the smaller to the larger. And now, this one we do have to solve by cross multiplication. But primarily because the variable is in the denominator, not the numerator. In other words, I can't solve for x in one step, but I can certainly cross multiply. Now the second step gives me x. And this is not a right triangle. That theorem involves all kinds of triangles. In other words, if I just made a triangle like this, and if I draw a line from there and it bisects that angle so that that's the same as that, and that's 2 and that's 10, and this is 3 and that's x, what equation can I write?
Would it be 2 is to 10 as 3 is to x?
Yeah. Making sure you're always going from smaller to larger equals the smaller to the larger. All right. Next one's a new page, I presume?
Oh, no, it's just on the right side of this page.
Oh, I'm glad I didn't get rid of it. Okay. I'm going to close it out and open the other one. 11.
So, hey, David, can we stop for a second on that theorem? What is the theorem again? In words?
If a line goes from the vertex of the triangle, any of the vertexes, and bisects that angle, then it creates two segments that are in the same ratio as the two sides of the angle that you bisected.
Okay.
Here's the two sides that you bisected, A and B. And I'm going to bisect this angle. By bisecting it, that's equal to that. Well, now I can say that A is to B as C is to D. That's the theorem. It's created the moment you bisect that angle with a straight line.
Gotcha.
Okay. Let's draw this. The pre-image is minus 6, minus 6. And I'm just drawing it approximately correct on my grid. That's A. B is minus 6, comma 4, which has to be about right there. That's B. And the third point is 2, comma 4, which has to be about right there. Now, if I could connect those dots, might as well, doesn't hurt anything. And now if I draw my other points, you can see that if I put them in blue, here's my A prime. Oops, hold on, excuse me. Not it either. It's right here. It's 3, comma 3. If that's 6, comma 6, then 3, comma 3 has to be about right there. And the second point is half of that. It's minus 3, comma 2, so it's right there. And the third point is half of this. So it's halfway, halfway. So it's like that. So that is my dilated figure. And this would be A prime, this would be B prime, and that would be C prime. What's the scale factor of the new figure?
Isn't it 1/2?
Yeah, 1 to 2. The center of dilation.
I'm not sure about that one.
Well, it's got to be the origin.
So it's 0, 0.
Yeah. And you get the center of dilation. In other words, if I connect that, it goes to the center of dilation. And same thing if I connect that, it goes to the center, and same thing if I connect that, it goes to the center. In other words, if you draw a straight line from each of these three original points to the center, you will find that A prime, B prime, and C prime are on those straight lines. They're the midpoint of those straight lines. In other words, 3 minus 3 is the midpoint between minus 6 and the origin. And that's a minus 3. You know how to find midpoints, right?
Sort of.
Well, let's talk about it, because that's maybe more important than dilation problems. midpoint problems are really going to be common. If I have minus 210 on one point, one end of a line, and I have 4 on the other end of a line, the midpoint is halfway between the x-coordinates and halfway between the y-coordinates. So what would this point right here be?
Would that be...
Add the two x values and divide by 2. That's the way to get it. Conceptually, though, it's very important you understand that this point, the x-coordinate is going to be halfway between minus 2 and 4 on a number line. There's minus 2, there's 0, there's 4. What's the distance between them? It's 6, but halfway gives you 1. Notice that 1 is 3 points, 3 from there and 3 from there. But the easy way to get it is just add the two numbers together and divide by 2. And that when you add them together, you get plus 2 divided by 2. There's the midpoint for the x-coordinate. Add the two y-coordinates together and divide by 2. There's the midpoint of the y-coordinate. Okay?
Okay.
In the last problem, what we actually had was the end point and a midpoint. So the problem became this. I've got a line that goes all the way to here, and I want to solve for that. What I have is this point, which is minus 6 comma minus 6, and I know the midpoint. The midpoint was minus 3 minus 3. So working the midpoint backwards, this has to be 0 comma 0, right? In other words, if minus 3 minus 3 is the midpoint, then the other end of it has to be 3 more units up and 3 units to the right, which puts me at 0 comma 0. And if I do that for each of these points, for B and B prime, knowing that B prime is the midpoint between B and some end, the end I get is 0, 0 for all 3 points. In other words, if I know that's the end of the point and I know that's the midpoint, I can figure out the other end is 0, 0. If I know that B is the end point and B prime is the midpoint, I can also figure out that the end point has to be at 0, 0. The same thing with point C. That's the end point of a line, that's the midpoint of a line, the other end has to be at 0, 0. And that tells me the center of dilation. All right. Which one do you want to do next? 12? What trig function do I use to solve 12?
Would it be sine?
Good. I don't need to write it out. So the way you always want to start your equation on these problems is the trig function of that angle. And you pick the right trig function because the pieces of information we had were the opposite side and the hypotenuse. Well, if you look at SOHCAHTOA, the only one that has opposite and hypotenuse in it is sine. So it's the sine of 32 degrees equals what?
X over 14.
So x is equal to 14 times this number. And that's all that is a number. You can get it out of your calculator. And you have to. That's the only way to get it. Okay? So the first step on these problems is always to set up the equation. Second step is to solve the equation. If you need specific answers on these, go ahead and put them into your calculator as we do them. I'm not going to worry a lot about the arithmetic. To me, what's most important is get you so you can set up the equation. I'm going to make the assumption that you know how to get this out of a calculator. What kind of calculator do you use, Patrick?
CI Inspire CX.
Okay. So you know how to do sine of 32?
Yep.
Okay. There's a trig button on that thing that lets you do all 6 trig functions and all 6 inverse trig functions. How about number 13? Which trig function are we dealing with there?
Cosine?
What's the equation?
Isn't it cosine 39 is equal to 22 over x? Or x over 22?
Which is it? What's this?
I think
What's that say?
adjacent over hypotenuse.
Okay. Now, to be fair, any angle actually has 2 adjacent sides, right? In other words, the 39-degree angle has a 22 that's adjacent, and the x is also adjacent. But in SOHCAHTOA, when they say adjacent, they're always referring to the adjacent side that is not the hypotenuse. So they're definitely referring to the 22. That's the adjacent side to that angle. So it's 22 over the hypotenuse, that. So how do I get x?
So would you put x cosine 39 equals 22 over cosine 39?
Well, this is the second step. You were correct. But now if I want to isolate x, yeah, I got to divide by cosine of 39. And that's the best way to do it. Don't come up with that number and then try to divide by an approximation of that number. In other words, once you get it like this, now in your calculator you can put in 22 divided by cosine of 39 and then round down. I don't see any instructions here on how many decimal places to round to. There a common one that he always uses?
No, not really. They just
round it off, huh? Because you can't, this is not like a radical problem where you can leave the answer exact as a radical. There's no exact answer other than what I've written. I suppose you could leave the answer like that if you wanted a really, really exact answer. But he probably wants you to give him a decimal answer. Okay, how about 14? Let me move it over here so we can see it. Which trig function relates those 2 sides?
it's tangent.
So what's the equation?
Would it be 10x equals 5 over 12?
Opposite over adjacent. TOA.
So it'd be 12 over 5.
Yeah, TOA. Opposite over the adjacent. So it's 12 over 5. Now how do we solve for x? If tangent of x is equal to 12 over 5, what is x equal to?
Would it be equal to 12 over 5? Or would it be
The inverse tangent of 12 over 5.
inverse?
Here's the thing. We use trig functions on angles to solve for ratios. We use inverse trig functions of ratios to solve for angles. For example, just go forward a second. If the sine of 30 degrees equals 1 over 2, which it does, then by definition, the inverse sine of 1 over 2 must equal 30 degrees. Okay? Notice up here, we've taken a trig function of an angle to get a ratio. But if we're solving for angles, we always have to use inverse trig functions. We're taking the inverse trig function of a ratio to get an angle. So you could have even immediately realized on this problem, we're solving for an angle, so instead of using the tangent, I can just go immediately into the inverse tangent of that ratio, and that's going to give me that angle. Okay? Now, you don't have to necessarily do it like that. There's actually an easier way to do this. When I have this and I want to solve for x, take the inverse tangent of both sides. Notice that what we now have on the left is just x, and what we have on the right is the inverse tangent of 12/5. Same thing, just a slightly different way to look at it. Whenever you take the trig function of an inverse trig function that's the same function, it always gives you whatever that is. So the inverse sine of x would give you x, and so forth and so on.
Okay.
15. Whenever you see a ladder problem, it's a right triangle. In other words, all I have to do is see one. If it's leaning against something, it's a wall, which makes that always a right angle. And this is the ladder that's 8 millimeters long. And they say that it makes an 84-degree angle with the ground. Which angle is that?
That's the angle opposite of 90.
Well, not opposite. It's the lower left angle. It's this one right here. Because it says the ladder makes that angle with the ground. They didn't say the ladder makes that angle with the wall, which would make this the 84-degree angle. But the ladder and the ground make an 84-degree angle. So now they want to know how far from the wall is the base of the ladder, which means that. So what trig function am I going to use? Am I going to use an inverse trig function or a trig function?
Trig function, cosine.
Correct. So what's the equation?
Cosine 84 equals, what would be x over 8?
Yeah, x over 8. And now, again, I can solve this. Because my variable's in the numerator, it's a one-step solution. So all I have to do is multiply both sides by 8, and I have my answer. When that variable is in the denominator, it's always going to be a two-step solution. You're going to have to cross-multiply as your first step, and then divide by one of the coefficients as your second step.
Okay.
So don't let these word problems be difficult. They're not. They're always triangle problems. That's all they are. Every time you see a word problem, especially in the context of trig, you're talking a right triangle. You just have to figure out how to draw it. And the ladder is always the hypotenuse, because the ladder is always leaning against something, right? In other words, the ladder is never going to be side x, and the ladder is never going to be the height of the wall. The ladder is always going to be the hypotenuse when you see a ladder problem. Okay. Now, all right triangles can be solved the way we've solved every problem so far, using one trig function, the angle, and the appropriate sides. But that only works for right triangles. Number 16 is a non-right triangle. Okay? And when you're dealing with triangles that are not right triangles, well, all of that stuff about adjacent over hypotenuse and everything, that's not even a hypotenuse. That's just the long side of the triangle. Definition of hypotenuse is opposite the right angle. There's no right angle in this. So this is a problem that requires the law of sines or the law of cosines. Now, let's not start right off with the law of cosines. Let's do the law of sines, and I'll show you why in a moment. Let's go down and do 17 first. Mainly because the law of sines is so much easier. In order to use the law of sines, I have to have at least one angle opposite side relationship. Do I have it in this figure?
Yes.
Okay. So what equation can I write?
Would it be...
Start with what you know. There's your angle opposite side relationship. That's 50 degrees, that's 45 degrees. So
would it be...
Go ahead.
50 over 22?
Sine of 50 over 22. Very important. It's not the angle over 22 that's equal to 45 over side B. It's the sine of the angle divided by the opposite side is the same as the sine of 45 divided by B. And it's the same of the sine of this angle divided by C. What's this angle? We don't need to do anything but subtraction to solve this angle.
Is that angle 85?
Yeah. So I can finish, if I want, and say that not only, and that's a number, notice. So in this equation, I only have one variable, B. Cross multiply and you'll get it as your first step. Okay? In other words, I would have sine of 50 times B equals 22 times the sine of 45, and then B is going to be all of this divided by the sine of 50. That's what you'd want to put into your calculator to solve for B. Okay?
Okay.
But that relationship is the same for all three of these angles and sides. In other words, once I have the fixed relationship, this relationship right here, sine of 50 divided by 22, I can also solve for C now. What's the rest of it to solve for C?
Would it be... Oh, it would be C, sine C.
Which is, we know this angle now.
So it would be sine 85 over 45? Or not over 45?
Over its opposite side. In other words,
So,
the law of sines has to do with an angle and its opposite side. And its opposite side is always, if you take both rays that create that angle, go to their endpoint, whatever the thing that connects those two endpoints, that's the opposite side to that angle. So little c is the opposite to 85 degrees. So that's where it goes. Notice that I had the sine of 50 over little a equals the sine of 85 over little c equals the sine of 45 over b. So by using just the law of sines, I can solve this whole triangle. Still there, Patrick?
All right.
Yeah, okay.
Yeah.
Okay, now let's go back to the first problem. Most problems you're going to use the law of sines on. Because most problems you get, and the reason, if I look at both of these problems over here, notice that the first thing I see on 17 is I got an angle and an opposite side. That's a law of sines problem.
All right.
Okay? Notice that if I go look at 16, I got an angle, but I don't have its opposite side. Then I got two opposite sides, but I don't have their angles. So there's no way for me to use the law of sines on 16 to begin with. All triangles, at some point, you do use the law of sines. But depending on the triangle, sometimes you start it off using the law of cosine. Now, the law of cosines is only used in two situations. So where you have side angle side, or you have side side side. With either of those two situations, you do not have an angle and an opposite side relationship, right? This triangle is side, angle, side. So we have to begin by using the law of cosines. Now, do you know the law of cosines?
No.
All right. The law of cosines says, and follow my pattern here, because that's what it is a pattern. It's a little like the Pythagorean Theorem, but then we subtract 2bc cosine of A. And there's actually three laws of cosines, depending on which side we're looking for. This is a squared plus c squared minus 2ac cosine of b. You see the pattern?
Yes.
What's c squared going to be equal to?
Wouldn't c squared be equal to a squared plus b squared?
Minus?
Minus 2ab cosine c.
Yeah. So they're all really the same formula. But in this particular problem, the side we don't know is side C. Let's back up a step here. What happened to it? No, it's over here. I hate Windows 10. Truly do. All right, so we're trying to solve for A, right?
Right.
Actually, it says completely solve the triangle. But the first side we can solve for is A. So I'm going to use this one. As I said, all of these are the same. And if they labeled this triangle differently so that that was B instead of A, well then I'd use this one. Okay, so
Okay.
what are my two sides? 12, 15, and 110. Now see, why does it do that? It shouldn't do that. I'm going to use that formula. A is the variable that I don't know that I'm trying to solve for. So A squared is going to be equal to what?
It would be 12 squared plus 15 squared.
12 squared plus 15 squared minus
2 times 15, times 12 times 15.
times cosine of what?
A.
Which is?
110.
Notice that everything on the right side is a number. So A is going to be the square root of that whole thing. And this, you just have to plug that into your calculator. Now you want to be a little careful when you do it, because it's fairly easy to get this wrong if you try to do it all in one step, especially if you try to take the square root of everything. it's real easy to make a mistake in the calculator. So I'm inclined to do these in multiple steps. In other words, figure out what that is, figure out what that is, figure out what that number is, and then go from there. You know what I'm saying?
Yes.
Now, without going through the math, just because I don't want to spend that much of our time doing arithmetic, if that's okay with you.
That's fine.
Okay. We're going to be able to come up with a number for A. Just for the heck of it, let's say we came up with 20. Okay?
Okay.
Well, now, notice that the rest of, we got 20 here at A. Okay? Whatever the number is, it's at A. Now, I still got two other things to solve for, right? I now know four things of this triangle, but you got to know all six. You got to know all three angles, all three sides to solve a triangle. Well, the rest of the problem I can do using the law of sines. In other words, the moment I get an angle and its opposite side, I'm not using the law of cosines again on this problem. The second step, I can use the law of sines, and let's just assume that 20 was correct. So how would I finish and solve for side or angle B?
Would you put
Use the law of sines. So what's the one relationship you know in that triangle? Assuming A is 20.
is it sine 110 over 20?
Correct? Equals,
Going to be sine.
I'm trying to solve for angle B.
So it'll be sine 110 over b.
Sine of B
Sine of b.
over 15. In other words, once you have this relationship where you have an angle and its opposite side, then no matter what angle you're dealing with in the triangle, this thing is always true. In other words, there's the sine of the angle divided by its opposite side. That's going to equal the sine of angle B divided by its opposite side. It's also going to equal the sine of C divided by its opposite side. However, once we solve for angle B, we won't need to use the law of sines to get that last angle. The easiest thing is going to be to just subtract my two known angles from 180, right?
Right?
So in a lot of these problems that you have to begin using the law of cosines, step 2 is the law of sines, and step 3 is just to add the angles and subtract from 180. So there's actually 3 different concepts you use when you start with the law of cosines. Now, before we leave this problem, let's make sure that you know how to solve that. How do I get angle B?
Couldn't you just cross multiply on this one?
Okay, again, I don't really need to cross multiply. I just need to get rid of this denominator. So how about we just multiply both sides by 15, and that gives me that. That's still a number. Now what's angle B going to be?
Going to be 15 sine 10 over 20.
Going to be the inverse sine of that. In other words, if the sine of B equals this, then the inverse sine of this equals B. Remember, these are just numbers. So to solve for an angle, which is capital B, I'm going to use the inverse sine. And again, when you take, I can, well, no, Yeah, that's good enough. Yeah. In other words, this comes out to be a number, and then take the inverse sine of that number, and you get angle B. Well, once you've solved for angle B, now you have two angles and all three sides. The only thing left to finish is that third angle. So take your angle A, take your angle B, add them up, subtract from 180, and that's angle C. Okay?
Yep.
All right. Looks like a good place to stop for tonight.
That was a good session.
Yeah.
Yeah, let me just check here when you have another one tomorrow night. Okay, cool.
Oh, yeah, you sound terrible.
Yeah, I am. But I
Really
feel about 300% better than I did 2-3 days ago, let me tell you.
Yeah, something really got you because you sound really got you.
Yeah. No, I thought it was just allergies, but then it kind of moved to my lungs, and
Yeah.
that's not more, it sounds more like a cold now than allergies to me, but anyway.
Sounds almost like pneumonia, so be careful.
I know, I didn't like it when I knew it moved to my chest. That's the danger for sure. But better than the thought that it's allergies and I should feel like this for a whole month and a half every time at this time of year. So anyway, I'll talk to you. Thank you. And I'll talk to you tomorrow night at 7:30.
Okay.
All right. Bye-bye.
Good night.